Hello everyone, my name is Xia Li. I'm glad to have you here. Today I'm going to talk about my research of robust perimeter control with cordon queues and heterogeneous transfer flows. The other two authors of this research are Dr. Mohammed from the University of Queensland and Dr. Mosen from the University of Sydney. The overview of my presentation is, first I will give background by introducing several terminologies, and then I will give description and contributions of this research. Then I will move to the methodology and the results, and finally I will close my presentation by summaries. Okay, now let's see some terminologies. The first one is two different representations of MFDs, the accumulation-based and trip-based MFD. For the accumulation-based MFD, it describes a nonlinear, low-scattered relationship between trip completion rates and vehicle accumulations when the spatial distribution of congestion is homogeneous. The trip-based MFD describes a well-defined relationship between regional speed and vehicle accumulation of a network. The trip-based MFD considers traveler details such as travel length, departure time, etc., whereas the accumulation-based MFD assumes all vehicles with the same travel length. Next one is perimeter flow control. Well, it's a kind of control strategy that always applies at the region boundaries. As you can see in this figure, U12 and U21 denote perimeter controllers. In the real network, perimeter control is implemented using coordination among traffic signals installed at boundaries between the regions to regulate the rate of transferring vehicles from one region to another to prevent hypercongestion. Okay, now let's see the description and contributions. This research is to develop an accumulation-based MFD model with uncertain parameters. Because in the real network, there might be lots of uncertain parameters that influence the model accuracy. For example, when we estimate the accumulation fractions from one region to another, the number of transferring vehicles is approximated by the ratio of the instantaneous number of vehicles based on their destinations. This is the assumption used in an accumulation-based MFD model to estimate the transfer flows between regions. But we will release this assumption by including uncertain parameters. Then we develop a robust sliding mode control based on this accumulation-based model and apply the controllers on the trip-based MFD model. The trip-based model is used to represent the real network to get more realistic values of transfer flows. Okay, now let's see the accumulation-based MFD model. And here are the conservation equations of this model. The explanation of variables are listed in the red box. Well, the accumulation-based model assumes all vehicles in the network with the same travel length, which is not consistent with the real network. Therefore, we consider to use a more detailed model, the trip-based model, as the real network. For the trip-based MFD model, it considers different travel lengths of vehicles, and the equations here calculate the travel length of vehicle I from region 1 to region 1 and region 2, respectively. So after introducing the two different MFD models, we need to ensure these two models are consistent since the controllers are designed and applied on different models. As shown in the figure, we utilized a slow varying demand, and the travel length follows exponential distribution. The accumulation evolution are shown in the right two figures. The two models are consistent in the trend of accumulation evolution, while the magnitude are not exactly the same since the trip-based models react immediately when there are demand surge. Then we apply random selected trip lengths. The accumulation evolutions of these two models are shown in figure A and B. We can see that when the system reaches steady states like after 2200 seconds, the two models are consistent. We also compare the uncertain theta parameters. Remember that in accumulation-based model, theta is continuous, and estimated through instantaneous accumulations. But this estimation is not always accurate. While using theta to estimate accumulation fractions might be reliable under some conditions, but it is less accurate under time-varying and complicated situations. So we need a robust controller to deal with the theta uncertainties in the accumulation-based model. For the controller design, we develop a robust sliding mode control to deal with system uncertainties. Well, I will not go through the details, but the process of applying sliding mode control theory in the perimeter control is shown here. To investigate the performance of the proposed controller, we develop an improved bound control strategy for comparison. The bound controller is an on and off controller that either let vehicles pass the boundaries or restrict all vehicles. Okay, now let's see the controller performance. A typical peak hour demand is applied, as shown in Figure A, and the accumulation evolution of no control scenario is shown in Figure B. As you can see in the figure, region 2 is the more congested region, since in no control case, the control inputs are always equal to the maximum values such that a few vehicles are queued at boundaries. As you can see, the values of queuing accumulations are very low in no control case. Okay, let's see, the top two figures are showing the accumulation evolution when applied improved bound and sliding mode control. And the bottom figures describe control inputs over time. As you can see, when apply improved bound control, the accumulation distribution are more uniform in two regions. But after 500 seconds, the vehicles are continuously concentrated because of the perimeter controller. For the sliding mode control case, it can be seen that the congested region becomes region 1, whereas it was region 2 in no control case. This is because the sliding mode control tries to protect the more congested region 2. While perimeter control could ease the network congestion to some extent, since the cordon queue sizes are higher when applied either improved bound or sliding mode control, such that more vehicles suffer delay because of perimeter control. The production MFD of region 1 and region 2 are shown in these two figures. We can see the hysteresis loops. Well, makes sense since the hysteresis phenomenon exists when the accumulation is uneven distributed in the network. In this paper, we consider cordon queues, so the distribution is not uniform, especially the queue sizes are large. The table shows the total time spent and the average travel time for the three control cases. The values in parentheses shows the reduction in total time spent compared to no control case. As you can see, the sliding mode control gives the best performance, around 22% reduction in total time spent. Okay, in summary, we develop a robust controller based on sliding mode control theory to address the modeling uncertainties in the accumulation-based MFD model. And a two-region trip-based MFD model is developed and compared with accumulation-based MFD model. Then it is utilized as the plant to investigate the proposed controller effectiveness. And we found that employing sliding mode control theory outperforms the improved bound in reducing the total time spent. Okay, that's all. Thank you.